Here's one of the top 10 reasons why statisticians are misunderstood. They are 99% confident that sleep cannot be induced in an introductory statistics class by lecturing on z-scores. Get it? Z and sleep. All right. So we will be using calculating probabilities for the normal distribution, and we've already learned about the shape. And in fact, we can already answer this first question. What is the percent of the population that is between 1 and 2 standard deviations taller than average? And that's assuming the heights of females are normally distributed. Well, before I do that, let's recall from our earlier lesson that we had this beautiful model, the normal model. And for certain values, like 1 or 2 or 3 standard deviations away from the mean, we know what percentages fall into those categories. So looking back at ours, we were like, what are the top, or I should say, the what percent of the population is 1 to 2 standard deviations taller than average? Well, that's this piece from the graph we were just looking at. So using the empirical rule, it is 13.5%. What's the probability that an individual female is between 1 and 2 standard deviations taller than average? It's the same as the area percentage. It's 13.5%, or 0.135. Now, assuming the heights of males are normally distributed, what percent of the male population is between 1 and 2 standard deviations taller than average? That's also 13.5%. Why are the answers the same? Well, when we use z-scores, or the number of standard deviations away from the mean, it's like you're scaling the pictures to the same size. So we scale different measures to the same units. Now, if I ask you, go ahead and shade in the area for the females between 1.2 and 2.5 standard deviations above average. And if we go ahead and do that, you see right here, and I ask you what percent of the females are in there, you would have a little more trouble because the empirical rule, which is what you know so far, only works for z values that are -3, -2, -1, 0, 1, 2, or 3. Now, the nice thing is your calculator can determine areas for any z-scores. If you tell it the z-score for the left boundary, which I'm going to call z left, and also could be called z lower, and the z-score for the right boundary, which is z right, you can also call it z upper. So it's referred to as upper on the calculator. So if we're going to calculate these probabilities, what you need to do is press second in distribution, and you'll see this menu right here. The distribution, in case you forgot which one it is, that's the VARS button. And we're going to scroll to this 2, which is normal CDF. And then you're going to get this screen, and you can put in the lower and the upper. So that's the left and the right boundaries. And then make sure your mu is 0 and sigma is 1. Now you can use x values here instead of z values. But when you're doing that, there's some of the shortcuts I give you, I'll let you know again, where it's a little trickier, but it can be done. But if you're using z-scores, which is what I normally do, these two values, the mean z-score is always 0 because you're 0 standard deviations away from the average, and our sigma is 1. So if you're using z-scores, this needs to be 0 and 1. If you're using x values, it can be the mean for x and the standard deviation for x. And these two would also be x values. Once you're done putting these in, you scroll to calculate and press enter. And it will then show you normal CDF with z left and z right, and then you see the 0 and the 1. Now, if you have an older calculator, you won't get this nice screen. It's just going to show normal CDF, and you just enter those values separated by commas and press enter to get the percentage or probability, which is right here. Now, if I want to determine the probability that x is between two numbers, I can just use normal CDF with z left and z right. So let's look at this example. We have the weights of newborn children in the U.S. vary according to the normal distribution with a mean of 7.5 pounds and a standard deviation of 1.25 pounds. The government classifies a newborn as having low birth weight if the weight is less than 5.5 pounds. The model is 7.5, 1.25. What is the probability a newborn will weigh between 6 and 7 pounds? So we're going to get the z-score for a 6-pound baby. And we learned the formula x minus mu over sigma in our last set of notes. And we get a z-score of negative 1.2, which would be about here. Z-score for a 7-pound newborn, well, it's going to be over here somewhere because the mean is 7, would be 7 minus 7.5 over 1.25, which is negative 0.4. And that would be here. So the area that we're looking for is between 6 and 7 pounds, so it would be between the two z-scores of negative 1.2 and negative 0.4. I can just go ahead and do normal CDF with negative 1.2 and negative 0.4, and I should get 0.2295. Now, if I had done this on the calculator where I had done 6 and 7, if I change that to 7.5 and 1.25, that's 0 and 1, then it'll work out okay. So that is the shortcut on the calculator. Personally, I expect you to be able to calculate z-scores. That's sort of a basic thing to statistics, so don't just only use x values. Also be used to using z values. All right, so if we want to find the percent of babies who weigh more than 10 pounds, we're going to go ahead and find and mark the z-score for a 10-pound baby. So let's find the z-score. It's 10 minus 7.5 over 1.25, which is 2. And we want babies who weigh more than 10 pounds. So that would be this area right here. So my left boundary is 2. But what would my right boundary be? In theory, this goes on forever. And we should really go to infinity. But infinity is kind of a big number. It would take forever, literally, to put it in your calculator, and then it would choke and it wouldn't work. So that's too hard. Let's just use a big number like 1,000. If you're using z-scores, 1,000 will work really well. If you're doing the x values in the calculator here, then you have to be careful that that 1,000 is not too small, all right? So let's go ahead and calculate for the z-score here. We got 2 and 1,000. You should put this in your calculator, and you should get about 2.28%. So the general rule is when you're trying to find the probability that x is greater than a number, you can find the z-score for that x, and that's your z left, and then just use 1,000 for z right, and you can leave 0 and 1 there because we're doing z-scores, and it will give you the answer. Now, if I had done, say, we have 2,500 students on average present during second period, and I'm doing x values, I'm just making up an example right now. I could do 2,500 here, but 1,000 isn't even less than 2,500, so I'd want to go to a really big number like 10,000 or 100,000. And then I could put in the mean attendance here, which, depending what it was, could be like 2,400. And then I could put the standard deviation there, which could be like 100. So that's, again, I'm talking about putting x values instead of z values. Again, I prefer z-scores. Now let's go ahead and look at the percent of babies who have low birth weights. And we'll go ahead and find the mark the z-score for a 5.5 pound baby. That's what's considered a low birth weight. So first I have to calculate the z-score, and I get negative 1.6, which is here. And I want low birth weight, so that's to the left. So on the boundary here, in theory, the left boundary is negative infinity. But we're going to end up probably using another substitute number. The right boundary is actually my z-score, negative 1.6. Now, since it's too hard to put negative infinity in our calculator, we pick a big number compared to this 0, 1, 2, 3, which is 1,000, negative 1,000. What percent of babies weigh less than 10 pounds? You can do normal CDF of negative 1,000 to negative 1.6, and you get about 5.48% of the babies. This is, so you can put in negative 1,000 to z right. That's a general rule, and that should say x is less than a number, not x greater than a number. So let's just do some quick practice on shading. Another thing, I want to stress how important, I'm going to go ahead and put these two in. I want to stress how important it is to draw the picture, at least while you're first doing these normal distributions. It really helps you keep straight what is a reasonable answer. So here I'm just going to do normal CDF with these two, and I get 6.38%. Does that make sense for this picture? Yeah, 6.38 is kind of small, and that area is not very large. If I'm doing negative 2.75 is less than z, there it is, and I'm really looking over here. So I'm going to do negative 1,000 to negative 2.75, which is a really tiny number of 0.3%. It's very small, and it does match our picture, so that looks good. If I want greater than negative 1.5, there it is. This should be a big number, more than half. In fact, most of it. And if I put those two numbers in the calculator, I find out it's 93.3% of the area. Between numbers is pretty easy. Just go ahead and mark them both. And you would say, that looks like more than half, but definitely less than this. And you would find out that this is 83% here. So 83% makes sense. It's large, but it's less than that 93.3% area. Let's do one more with z is greater than negative 1.2. So I'm going to the right. See, this is the right area because I'm going greater. So negative 1.2 to 1,000. And I get 88.5%. That makes sense. Z is less than negative 1.2. So I would do negative infinity to negative 1.2, and I get 11.5%, which also makes sense. It's less than half, and it's this side. If you're prompted to use tables on your assignment, you may use your calculators instead, but please note there might be some slight rounding differences, so you might want to adjust a little if you're doing like the thousands or 10,000s on the units.